Nuclear energy is one of the cleanest alternatives to fossil fuels. It harnesses the power of nuclear fission for use as electricity. Nuclear fission is the process by which an atom splits, releasing free neutrons, gamma radiation, and a tremendous amount of thermal energy. When an atom fissions in close proximity to other atoms, the free neutrons are absorbed by the other atoms, causing them to fission. This is called a chain reaction. Only very massive unstable elements, such as uranium, can sustain a chain reaction and are used as nuclear fuel. To convert the nuclear energy to electricity, the nuclear fuel is submerged in a pressure vessel filled with coolant water. This goes through a steam generator and drives a turbine to generate the electricity. We measured the output of the reactor using a phenomenon called the Cherenkov effect. The Cherenkov effect is similar to a sonic boom, but with light instead of sound. When an object travels faster than the speed of sound, it creates a shock wave that can be heard as the boom in the wake of a supersonic jet. Cherenkov radiation is released when a particle moves faster than the speed of light. Nothing can move faster than the speed of light in a vacuum, but in a medium like the coolant water, light moves more slowly. Particles given off by the reactor can move faster than the light. The energy this creates is released in the form of high-energy photons, which are visible as a blue light. The intensity of this light can be measured to determine the output of the reactor.
The first step of the engineering design process was to ask. Our problem was to interpret the power levels of a nuclear reactor. The constraints were that we must interpret by measuring Cherenkov radiation.
So the next step in the engineering design process is to imagine. So we asked how. We would do this by using PVC pipe, creating a circuit with photodiodes or photoelectrodes of some variety, and then waterproofing the photodiodes so they didn't short, but you had to maintain transparency too, so the light could get to the photodiodes. So we chose to use 1.5 inch PVC pipe, 4 photoelectrodiodes in a parallel circuit. We would solve the water problem by using silicone sealant and transparent plexiglass on the cap. So the next step was to actually create the nuclear probe. And so what we did was we went down to the craft center, and initially we just twisted the photodiodes together and made it connect with some electrical tape to the actual wiring itself that goes up to the voltmeter. And we weren't getting anything, no readings at all for the light. So that was a failure.
So the next step was to improve our probe. We decided to simplify and use just one photodiode in a series circuit.
So this simplification ended up working pretty well, as our team ended up second in the competition with only a 2.4% error. The actual kilowatts that the nuclear reactor was putting out was 250 kilowatts, and our probe measured 256.1 kilowatts. Overall, we got second. It was pretty good. One of the biggest design challenges that we faced was after we switched to the simpler circuit, we decided to solder the wiring together. And it turns out that over a long wire like that, the electricity shorts on the negative side. And so for a while there, I thought we weren't getting any readings from the other end where the multimeter goes. But it turns out that we were getting it. It was just shorting out if you were really close to the soldering. So that had my head spinning for a little while. That was really challenging.
What we would do differently if we had another chance is really sit down and look at our calendars and look at everybody's schedule and just pick dates where we can get together early on, because those due dates really sneak up on you, and it's really important to manage your time well if you want to be successful.
As far as advice goes, I would also say that you should really use your professor no matter what project you have, and also to go ahead and start creating your project at least a month beforehand, because that way you can troubleshoot, and there's always something that goes wrong with these projects. So get started early. I'm hearing. Okay. Ready? Set. I'm recording.
Now this is a story, so listen, son, to hear what we did for E101. So I'd like to take a minute, just stay right here so we can show you what it means to be an engineer. On Centennial Campus, born and raised, working on this project's how we spend our days. Planning out, diagramming, soldering too. Not just anybody can do this, fool. When our professor, she was up to no good, started making trouble in the neighborhood. She gave us one too many assignments on top of this job and turned our class into an angry mob. So we worked and worked, day after day, but it felt like this project wasn't going away. We gave it one last shot and decided to quit, but then we worked it out so we could submit it.
Second place, yo. That's not bad. This nuclear probe turned out to be rad. That's short for radiation. Catch that nuclear pun? Who said FEDD? Can't be fun. But wait, want to hear about the engineering design process? You gotta ask, imagine, and plan to impress. Create and improve, and that's all there is to it. Compared to those chassholes who don't even do. Well, it was cold that day at the start of winter when we presented our probe at the McKimmon Center. We're not trying to fail yet, we just got here, but our probe looked way cooler than the projects that were weird. We measured the amount of light that was emitted. Yeah, you could say our team is committed. If anything, we waited for half a year, but then Marshall told us we were great engineers. We got out of the center about 7 or 8. It was cold and rainy, but we felt great. We looked at each other. It was finally done. Wrote this rap as a rap, ending with a pun.